The first paper is enhancing non-English conversational agent use synthetic data generation. So, okay, who will present? Can you come? Sala. In this section, every paper has the 5 minutes and also have one question, and then we move to next. Okay, this is short paper. Okay, can you start? I will control 5 minutes.
Hello, everyone. My name is Salar. I'm presenting Enhancing Conversational Agent with Data Augmentation for Multilingual Applications. So imagine in a world that there are online support groups, but there is so many problems, such as it's difficult to find people at the same time to have a session with them. They have a stigma, so it means they're not so open to talk about their problem, especially in healthcare domains such as HIV, smoking, or this kind of things. It's even hard to recruit peer-led support, and there are like low engagement for the people because we have difficulty in finding people. Also, we have difficulty in scheduling conflicts between them, and there is also language barrier for non-English speakers. So online support group has so many problems that we want to solve it through smart chatbots. Our solution is to use multilingual chatbot with improved accuracy because, as you probably know, LLM are doing very good work with multilingual things, and they can easily translate everything in non-English languages. And the other solution we have to increase the accuracy is the data augmentation, because we're currently using RAG, but in order to make it better, we need to have like synthetic GPT generated prompts to create real world solution for the scarce data that we are facing problem with. Because in some labeling and groups we have problem, and the problem is we don't have enough data. So we are generating GPT generated prompts to create real prompts, and then we use these synthetic prompts to scrape data from forums that are talking about healthcare domain. To do so, we are using fine-tuned Llama and XLM Roberta because they're one of the best multilingual LLM, and we compare them with GPT-4. To do so, we first do the synthetic augmentation, and we create the prompts for low-frequency intents. After we are doing this, we are finding these synthetic prompts to the real website that are presenting some data, and then we are scraping them and augment the data set with both synthetic and real data. And after that, we are trying to improve training data with the diversity and realism. So the key result in the English phase is increasing 32% the F1 score with combined augmentation system, which is like 87% for the synthetic data. We have high quality. And also it outperforms older models like BERT or existing healthcare domain chatbot. As you can see here, for the multilingual phase, we have like Spanish, Chinese, Arabic, Hindi, and Farsi. And as you can see, the result of the GPT-4 are in the green bars. They're good enough, but as we cannot use any kind of things like augmenting GPT-4 still, so we need to use other model that we can augment it. So the result shows, for example, for XML, the blue one is not good, but when we are using the augmentation with both translated and scraped real data, it goes comparable to GPT-4, and for Llama, it's even better. It's probably the same for all language, and it shows that the F1 score can goes up even with the comparison with GPT-4 after we augmenting. So it shows that the multilingual intent classification is a robust model, and we are planning to expand the language and cultural adoption of everything related to different language, and the target deployment is public health platform and social media. That's it. Thank you.
Any other question? One question?
Cool.
Okay, cool. Okay, let's move to the second paper. Second paper is automatic chest X-ray image caption for report generation.
Hello, everyone. Thank you for being here for my presentation. I am Jialu Li from the Master of AI program at Yeshiva University. Today, I'm presenting the paper, The Automatic Chest X-ray Image Caption for Report Generation. As you know that for clinicians, generate the reports, the direct diagnosis from the radiology images directly, and then generate report from scratch is time-consuming and error-prone, which also requires professional activities. Therefore, like the automatic medical report generation is essential in the automation process in the medical fields. And it is also an advanced applications of the automatic image captioning, although that requires more accurate image classifications and the professionalism of the wording choice during report generation for the applicable medical use. And there are currently some of the popular architectures for the automatic report generations, including the encoder-decoder architectures and the RAG, retrieval augmented generation architectures. However, the existing models there currently face a couple of challenges, such as the description inaccuracy of image findings. This includes like the inconsistent finding from the generated reports with the original images. And there's also like the challenges of the data insufficiency and imbalance, which challenge the training of the deep learning models. And therefore, the research aim of our paper is to provide a model that can improve the performance of the automatic report generation and with the vocabulary training set. Our paper used the IU X-ray datasets from the Indiana University, which is a publicly available dataset with the human chest X-ray images and the associated clinical reports. And we developed a preliminary model, this ResGen, which is an encoder-decoder architecture that leverages the ResNet50 as the image encoder, and the GPT-2 as the text decoder. And we also include an multi-head attention block, which is to help the models to better attend the relationship and the dependency of each of the image features before passing it to the text decoders. And we also include a training the vocabulary training set, which can help the models to better understand the text features that's passed into the models before the decoding the image features. And our paper reports the results on the comparisons of the state-of-the-art report generation models and with the RAG models and our proposed ResGen models. And we can see from the table below that our ResGen models produce a higher metric performance compared to all the other state-of-the-art models, except for the blue one scores. This indicates that our preliminary models with the vocabulary training sets can outperform the state-of-the-art models in the automatic report generation task. And here's also a demonstration of the comparison of reports generated from ResGen models and the RAG Llama models. We include the original images and the original reports that's from the datasets, as well as the generated reports from the ResGen models and the RAG Llama models. We can see that compared to the RAG Llama models, the reports that generated from it, the ResGen models can produce a report that is both accurate in the conclusion, but also more similar in the text in the wording selection compared to original reports. However, we can see from the second like the examples that the reports that generated from our ResGen models actually facing the problem of the incomplete text structures. As we can see, it's not the fluent sentences. And this is, of course, the challenges most of the models that faced recently. And therefore, in conclusion, our developed model, ResGen, showed state-of-the-art performance in automatic report generation compared to other state-of-the-art report generation models with the help of the vocabulary training app. And in the future, and we also plan to continue to explore the state-of-the-art image text architectures to improve our preliminary models to make it a more advanced vision language models we can help to be applied in the real world scenarios, so that the clinicians can directly refer to the preliminary reports generated from the models and then just revise it based on it, which requires a more accurate conclusion, whether it's normal or abnormal, instead of just the text similarities. And this is a long way to go for the AI applications in the medical field. And thank you so much. I welcome any questions.
Any question?
Okay, thank you.
No question? Okay, let's move to the third paper. Third paper is DF-RAC, a dual federated retrieval augment generation framework for collaborative medical AI.
Hey, good afternoon, everybody. So today I'll be talking about dual federated retrieval augmented generation, a framework for collaborative medical AI. My name is Michael Zajac, and I'm currently an MBA student at the University of Alabama, and I'm doing research for the AI lab here. So the first thing we'll take a look at is the motivation of the problem statement. We all know that large language models have the problem with hallucinations. There's the privacy risk because you're sending your data out to OpenAI or Google or whoever, and you don't know what's happening with your data. And then the final thing is that there's low collaboration, because it's not the healthcare professionals that are training the models, it's the machine learning engineers. So our focus is a framework that prioritizes collaboration to mitigate these hallucinations, ensure privacy, and then increase accuracy and generalizability. So our objective here is collaboration. That's the most important key thing. So the first part, one of the first solutions that we looked at is federated fine-tuning. So we went ahead and looked at 5 different methods here, and we found that Flex LoRa was the best, the one on the bottom. And the reason was because that it was adaptable in the healthcare domain, because different health institutions with different scales of compute are able to add to the aggregated weights of the model. And so how it works. You start with the pre-trained large language model because you don't want to be, hospitals don't want to be training from scratch. And you do the local adapter training for each of those healthcare institutions. You encrypt that, you transmit it, you do a weighted average. And then the special thing about the Flex LoRa is you do the singular value decomposition so that each hospital, depending on if you have more compute or less, can provide to the aggregated weights. And then you redistribute that and you iterate. So more of a visual example right here. Each of these health institutions sent that global large language model. They do the fine tuning, and then they do the singular value decomposition. They get sent those re-ranked LoRa matrices, and then it iterates. The second thing that we looked at was the utility of knowledge graphs. And we really found them fascinating because they're able to show the relationships among many concepts. They're very specific to the medical domain, especially when you need accuracy and contextualized information. So we looked at the ontology, which is a schema with the domain expertise, which can be created among many different health institutions. So they can all collaborate on that conceptual schema, but they add their individual data instances to it. And when you query from one of your health institutions, the queries are federated, meaning you ask a question, ask that same question to all the different knowledge graphs. And so that context is retrieved and it's verifiable and traceable. You just get the union of those top embeddings. And so the framework is the combination of these two things. the federated fine-tuning and the federated knowledge graphs, which brings together the dual federated RAG. So we use the strengths of one to combat the weaknesses of the other. When we look at the federated fine-tuning, the strength is inference. You know, it's natural language, it's very easy to understand. But the weakness is the hallucination. When you look at the federated knowledge graph, the strength is that it's grounded in real data, but the usability is low. You can't ask questions in natural language to the knowledge graph. And it doesn't have, if you just a regular large language model, it doesn't have that, you know, intuition of the medical expertise. And so we're gonna fight the weaknesses of one with the strengths of the other. And so the full framework looks like this. Each of these are the fine-tuned large language models, which we saw in the previous diagram. Somebody sends a query out, that gets federated, so it gets split apart to each of the individual knowledge graphs. And then that query, or the queried information gets aggregated into a context. And to ensure that we don't share data that is confidential, of course, we're gonna wanna blur that stuff with differential privacy, or like my colleague previously presented, the approximate knowledge graphs. And so that aggregated context is going to come back to the fine-tuned large language model so that the answer is better. So you have both the intuition and the grounding. So just doing a quick evaluation, just looking at some qualitative metrics here, like the security. We're assuming the security is high for all of them just because we assume that these are all locally hosted models. So the privacy is high. The collaboration is the highest for this one because people get to work on both the ontology and then the fine-tuning aspect of the RAG pipeline. And you know, this one performed the best, especially on a scalability as well, because like I talked about earlier, the singular value decomposition, you get to send those re-ranked matrices, and hospitals with a lot of compute can be on the same level or similar level as the ones with the lower compute. So the benefits are a better diagnoses because you're working with better data, or more data, and it's privacy preserving and it's scalable. The concerns is conflicting information, because if you query, you might get different information across some of the health institutions. So that's where the human in the loop is still definitely essential. You still want that medical expertise, but there's been some other methods proposed, like some attention-based methods. Which one should we pay attention to more? Which information should we pay attention to more versus the other? And then the future work is to do some real-world pilots. What we're doing in the lab right now is working on some of the healthcare data sets. And actually, when we've done this federated RAG pipeline, the answers that are retrieved are very accurate. Because if you just do the regular RAG, the problem is that you might get some similar answers, but they're not the most relevant answers. But here, with the federated pipeline, you'll be getting more relevant answers. So thank you, everybody, for listening to me, giving me your attention. Yeah, any questions?
Yeah, any questions?
Thank you. Really interesting presentation. And this isn't, I don't really know much about this stuff at all, but you said you were doing your MBA. So I wanted to ask, like, why would a hospital with a lot of compute want to, like, if they're not in the same kind of center, why would they help someone, a hospital that doesn't have as much compute? I guess, like, how do they benefit from that? If I understood the presentation, maybe I'm completely missing a point here.
Yeah, great question. So you're saying, why does the big hospitals even want to work with the smaller ones?
Yeah, basically.
Well, if the intention is to cure disease and help patients, then they would want to have more information so they can make better decisions. And especially when it comes to maybe, let's say, one hospital is in a demographic where they only have a certain demographic of patients, like let's say New York City. But if you take a look at patients in rural Alabama, those might be different patients with different types of diseases. So in the case that they get a patient that comes into the big hospital that they don't have a lot of information on a certain disease, if they have the information from Alabama, that would be really useful for them to help that patient that comes in. If that answers your question.
Hi, Michael.
Hey.
So this is information. Okay, this is data that's dealing with like sensitive thing. It's health. First of all, how easy was it to get the data? How good is the data, and how is like the regulations around? Because some things to do with health are heavily regulated. Did you meet such problems in your work?
Yeah, so in our research, right now we're only dealing with the public data sets, right? So we haven't experimented. That's why, my future work, I said that some real world pilots would be great, collaborating with these health institutions. But right now we're just working with the public data sets, like some of the surveys as well, like MEPS, NSDUH, and all those. And but yeah, it'd be really interesting to take a look at how it's different to work with real health institutions versus some of those public data sets. Thank you.
Okay, next one. Okay, next paper is the two-modality approach for contactless value sign monitoring, use camera and Wi-Fi CSI. Okay, so first I introduced the motivation. We can use the different sensors like Wi-Fi, RFID, radar for the vital sign monitoring, like respiration or heartbeat. And definitely this is very important and for some like disease detections. And this is also have some advantage compared with traditional wearable device. And for this paper, we need to consider to use the Wi-Fi and camera together to provide the more confident the solution for the respiration monitoring. Okay, what's the challenging part? If you use the wireless or use the radar, it's very challenging to adapt to the different like noise or interference. And if you consider the camera-based, first definitely have privacy issue. Also consider a struggle in the like a low light or in the dark area. And motive is this, and we need to consider, can we use the different sensor from the Wi-Fi and from camera like a complement each other to improve the performance for the respiration monitoring and detection. Okay, first quickly introduce what is Wi-Fi CSI. Wi-Fi CSI that in the physical layer, it can reflect like the signal travel between the transmitter and receiver, can capture some like a scenario of the movement in this room. And also for transition, we can use the size, amplitude, and phase for some sensing, which can capture like some like a movement, small movement, and a bunch of the wall and the object. And this is just formula for the complex CSI value. In this work, we need to consider the architecture, use Raspberry Pi and the camera to collect data. And in the up bottom figure to show like the CSI over different subcarrier and over the time. And the right one also show the camera like a respiration like results. And based on that, we can extract feature and design the ensemble modeling for the different like respiration model classification and to extract the respiration beat. Okay, first, this is also we consider to use current like Wi-Fi router, set up the two Raspberry Pi device. One is to pin the router and also another one to set to the monitor mode to collect the CSI value in the physical layer. And okay, on top of this architecture, we can get a CSI, and at the same time, and our second respiration Pi with another camera in the one computer, also at the same time to collect that image data. And we can also use the motion-based respiration with camera for this. And another way is we quickly show that model for example, also use very simple like a convolutional neural network for the the CSI model, same model. And the second one is also we consider the simple like a camera-based model and include like a convolution 1D and also the bidirectional STM. And after that, we merge that together to design. You can see for the ensembling model for the 4 different respiration like structure recognition. You can see the final density 4. And also here is to show implementation. We can use Nesmo. This is a very good tool to collect CSI to support like a IEEE 811 AC device. And also we use the CSI kit to collect or process the CSI data set. And another one is also for camera data set, we use the a video magnification solution to detect the chest movement. And after that, we can collect that smooth respiration and for the Wi-Fi signal and the camera signal. And another thing is we first to show we consider the different respiration mode. For example, like a fast breathing or the slow breathing or like breathing holding or normal breathing. There are different patterns over the Wi-Fi side data collection or different carrier. And second thing is that also we compare the Wi-Fi CSI and the camera for the different this fast breathing, and you can see that is the high frequency for the respiration, and also slow breathing signals for the left and right. You can see there is the longer duration for the respiration for both of the sensor. And also we hold, after time we hold, you can see this is no periodic signal for both of all include the noise. And if we consider normal breathing, also we can get good results. And first we collect this data, denoising the respiration from the camera and also from the Wi-Fi CSI. And we use our different model. We design the Wi-Fi model, we have camera model, we have ensemble model. We found that our ensemble model can get better results compared with others. Okay, last one is I will summarize. This is the work we first used both modality Wi-Fi CSI and also the camera for the respiration monitoring. And also we design like a different model, like for camera model, Wi-Fi model, or ensemble model for the a respiration activity recognition. We also show this our solution increase that prediction accuracy. And on top of this workshop, our furthermore work we need to consider use a different model to denoising you can see the special Wi-Fi CSI data, and we can improve the SNR for the Wi-Fi and a camera to enhance that. If we get the clear high quality data set, we can improve prediction performance. Okay, thank you. Any question? Okay.
Thanks for your presentation. And I have a question about, because you combined the data from the camera and the CSI. So how do you handle the synchronization issues of these two?
Yeah, thank you for this question. First, in this presentation, I just introduced high-level idea. Definitely, we need to, for example, do the downsampling and to synchronize this from the image and also CSI this pattern. And there are some basic signal processing with signal processing to synchronize this CSI. For example, to make sure you have the similar frame and for the data to get feature and fit neural network.
Okay, thank you.
Okay, any other question? Okay, no. Let's move to next paper. Next paper is the MA. That marks the impending-based image augmentation with diffusion model for the enhanced demorphology image classification. Okay.
Okay, so today I'm going to introduce our work called it's called the masked imprinting-based image augmentation with diffusing models for enhanced dermatology image classification. So basically, we know that AI is particularly promising in dermatology. You know that in 2024, the US FDA, they have approved the first AI-powered skin cancer detection. Actually, the device is called the Derma sensor. So actually, we can purchase that nowadays. So this device is claimed to have reduced the missed cancer diagnosis from 80% to 9%. Although very promising, but the problem is that the AI performance in dermatology is actually limited by the quality and the diversity of the training data. So basically, there are two things: is that if, usually when you collect the data are kind of, especially in some rare disease, it's kind of small and scarce because, collecting the high quality expert annotated skin disease images is kind of a major bottleneck. Another thing is that, in most health conditions, the negative examples are well represented. You can collect as many as you want, but however, the positive examples the numbers are limited. So because of those limitations, if you develop an AI model without kind of a very good data set, this can lead the models that are less accurate, less generalizable, and also potentially unsafe in real-world clinical settings. So in this paper, our idea is that whether we can, kind of use the data augmentation to address those kind of challenges. In particularly with the data augmentation, is basically like you have some unlimited amount of data, and then you use data augmentation, you can create more diverse data, more examples like that, okay? And while using this augmentation, you can get more data, more diverse data, so supposedly when you train a model, it should be better. Okay, and we are exploring, there are many methods to do the data augmentation, especially nowadays, the random cropping, those kind of adjust the brightness, those are kind of standard practice. But nowadays, because of the popularity of diffusing models, those kind of things, we are trying to say, okay, whether we can leverage these diffusing models to generate the image, especially the skin images for us on demand. Okay, and on the right-hand side, you can see that there's a kind of the text. There are all kinds of text-to-image tools. So you give them a text prompt saying that what kind of image you want to generate. They will be able to generate kind of very real images, realistic images. Okay, so. But if we want to directly utilize those kind of tools to the dermatology, we feel there are two kind of challenges. The first challenge is that while they are kind of still, there's still kind of a large distribution gap between the generated and the real world data because they are still, this synthetic data is not the real data, right? There's still kind of a distribution gap. A second thing is that, if you want to use the text to image tool to generate the image, then you should have a very good prompt, okay? But most of the time, especially in the medical domain, describe those kind of describe the disease or the image that you want to generate in an accurate language is very complicated, okay? So motivated by those two challenges, we propose a work that we trying to, first improve how can we generate these augmented images. Okay, and the second thing that how can we leverage these augmented images? Those are two steps. So in the first step, in order to generate some images that is as close to the real images as possible, so we use a kind of called domain adaptation through the LoRa file tuning. So basically, we have some pre-trained diffusion models that has been pre-trained on some public image data set, and then we just use this kind of file tuning methodology, LoRa, to trying to adjust this diffusion models on those specific data set, the skin images here. Okay, so after we do that, so we can get a kind of reasonably well generative models here and diffusion model. But as I mentioned, there's always a distribution shift, right? So you need to worry about that in the next step. However, but at the same time, we want to say, okay, as I mentioned, it's very hard for you to describe the images in accurate language. So that's why we use this kind of a controlled augmentation through the inpainting. So basically what the inpainting do is that we have, for example, the right-hand side, the left-hand side, we have some real images that we get some kind of, we just do some inpainting to add some kind of random mask, and then ask the diffusion models to fill in this kind of random masked regions of the original image. So that's what we do here. And by using this one, we can say that in different runs, you may get kind of different types of field results, but we can leverage all of them because they can increase the diversity in those kind of areas while preserving the original information. So after we get the augmented images, well, these augmented images, they're still, okay, no matter what we do, they still can some distribution gap. So in this case, how can we leverage this augmented data? Well, standard way is that, well, okay, I just put the real image with the augmented or synthetic image together and just use the random shuffling and then just train a model. So that's the conventional way. But we found that the performance is not very good just because of the distribution shift. Okay, so we propose a two-stage training strategy. The first stage is that, well, we just first pre-train the model on only the augmented image, the synthetic image, right? Because this is just a pre-training stage. We don't need to be that accurate, okay, because we are going to adjust them later. Okay, so in the second stage, after we pre-train that, we're trying to fine-tune these pre-trained images on the original, authentic, the real images. Okay, so we tested that and found out this two-stage training strategy is much better than just a one-stage training strategy. So here's the experimental result. So basically, we leverage a public data set called the HAM 10,000 data set. So this just contains, we just randomly pick 10,000 images, which has been categorized into 7 different kind of categories. So we consider 2 classification scenarios. One is the data imbalance scenario. Another one is the scarcity scenario. So for the data imbalance scenario, basically means that we just randomly pick those manually pick those images so that, for some, for example, for the positive examples, we have just the 10%. For the negative, for the negative example, we have 90%. This is highly balanced data set. And we just compare different for this table here, the top right one. So basically, we consider different architectures as the pre-training model, and then we compare our method. The MIA is our method. The real is just using the real images to do the training. For the diffuse max and DA fusing, they are more like the state of the art in this area. So we found out that our performance in terms of accuracy and F1 score is also is better. Okay, and consider the scarcity scenario. Basically means that we already have very, very limited number of data, okay? So in this case, you can say if you train just to use this limited amount of data, the accuracy and F1 score are pretty bad. But however, if you use our MIA, well, at least compared to the existing data augmentation method, our performance is much better. So you can see that this shows that the effectiveness of our approach in both data imbalance, highly imbalanced scenario and limited data scenarios. So that's what I want to share. Thank you.
Any other question? Okay, I have a quick question. So you used different model to enhance that data quality or quantity. So how to distinguish that what's the difference between your sensor data and original data? And also, for example, if we just use a rotation and noise, what's different between your work and also traditional method?
Yes, basically, if you just, as you mentioned, the rotation and those kind of random cropping, those kind of things, they are the diversity, the generated images, their diversity is still very low because you just consider those kind of simple augmentation method. So we compare actually in the table that I just showed the real images. By default, we will use those kind of random, those standard data augmentation techniques. And by adding because the diffusing models, we are using some pre-trained kind of knowledge, right? So that basically means that we leverage the knowledge from some kind of public data set. So they supposedly should be able to kind of generate more diverse and realistic images.
Okay, thank you. Okay, let's thank the speaker again. And next one is the Curinite and combining uniform representation for efficient chronic disease prediction. Okay, you can start.
Hi, hello everyone. Thank you for participating in this conference. And my name is Juan Ding. I'm a second-year PhD student, and my topic is the Curinite combined unified representation for efficient chronic disease prediction. And our data set is collaborated with the Taiwanese hospital. And I will introduce the background because in Taiwan, the chronic disease is frequently correlated by longitudinal progression by development for the under comorbidity, and the traditional method like the statistics or the machine method they not consider the longitudinal of the progression of the chronic disease, and more of the research focus on the single model approach for the disease assessment, like the clinical notes, or the lab tests. But in our approach, our idea is to combine the two modalities for the chronic disease for diagnosis. So our approach is to propose the multi-model fusion, and how can we leverage the structured and the unstructured data to improve the precision of the chronic disease. And the second challenge is how we can leverage the fusion method and combine the two modality in the common space using the multi-model large language model. So our database also include the 10-year longitudinal data sets, and in this research we use the 5-year data sets, and our data include over the 1 million and 300 lab test results, and more the 1,000 of the lab test items. And these two modalities include each of the apartments in our database. So in the traditional method, they all only focus on stack of the chronic disease prediction, but in the clinical situation, more of the chronic disease will consider the longitudinal situation, because each patient will have different visits in the hospital, and they have the different situation in the clinical notes or the lab test data or others their situation. So we also consider time interval in the different patient visits in our time schedule. So potential chronic disease are cross-linked past medical visits. So in our proposed multi-model embedding iteration of the features, we first fine-tune the areas on the structural tests in the medical reports, and second part is the lab test data. We textualization of the each lab value to the test, and combine concat the two modalities to the test representation for the common modalities space. Then we also consider time scale in our model. We use the attention-based model and the different time visit the embedding in our module concatenation of the features. So we also, in our proposed model, we also consider temporal patterns analysis and the cross-model fusion in the unified patient representation. Then we apply our model in the public and the private data in our model. You can see in our result, the burst is not enough to handle the two modality, and we also fine-tune the LoRa-based Metro 7 model and the common-based Llama-based model, and compared to our coordinate model. So in our proposed model, you can see significant improve in the two data sets, include the private and the open data sets. So in a conclusion, our data sets, our model can achieve the 94% accuracy in the chronic disease prediction, and multi-model integration of the EH data, and also in our model also consider the temporal pattern in the model design, and we also validate in the two data sets, and in the model impact, the coordinates also combine the large language model with the multi-model in the chronic disease. And in our current work, our paper also assay to the SDA law. We consider the more promising framework to the disease planning, because in the traditional language model, they cannot be handle the planning test, because when you go to the hospital and doctor will write some diagnosis for you, but the currently the language model cannot handle the past medical history according to your personalized situation. So we propose a two-step model in our this framework to generate the disease diagnosis and planning for your next visit or for the doctor diagnosis. So thank you for your listening. Yeah.
Any question? Okay, thank you. Okay, next paper is Bridging Gap in Mental Health Support for Individual Experience Homelessness. A multi-stakeholder evaluation of the CHASE large language model powered chatbot. Okay, you can, okay.
Hi, everybody. I'm Li Ying Wang. I might be the only clinical psychologist in this conference. So this might be a breath of fresh air. Feel free to close your AI and machine learning brain because there's no mention of that in this presentation. Anyways, let's get started. For a background, for people who experience homelessness, they have very high burden of mental health. Here are some on the slides. At the same time, they have a lot of access barriers, including stigma, high cost, and lack of insurance as well. So in the context of in Florida, Tallahassee specifically, where Florida FSU is, Carney Center is a local shelter that right now is facing high demand and staff are reporting high burnout rates. This center usually provides emergency shelter as well as long-term housing assistance as well. So as you would imagine, these staff members here have a lot of demands coming from clients from different domains of their life. So CHASE Chat is a community initiative coming from Carney Center. We are aiming to work together as a team to develop CHASE Chat that can support navigation services and mental health resources support, referrals, triage for population experiencing homelessness in Tallahassee locally. All right, so there's a larger project, but today I'm going to present the results from AIM-1 needs assessment. Very qualitative. We conduct a couple interviews with our stakeholders. There were 20 clients who were living and residing at Carney Center, and there was one leader who is the CEO/director of the center, and also 6 staff members who are on the floor and working day-to-day with our clients, providing services. Okay, so 4 themes arose from our interview. We'll go through them one by one. The first one, so mental health and behavioral health needs are real. Our clients and staff, both, they all talked a lot about the struggles they face, specifically because of lack of access or limited access to treatment. Staff members are the ones who are left to deal with a lot of the mental health struggles our clients experience. There are a lot of crisis management, people with severe mental illnesses, such as schizophrenia, psychosis. Usually whenever they have an episode or behavior disruption, our staff members would have a hard time containing the situation while trying to provide support for the rest of the clients. So theme 2, barriers to access services and case management challenges. Clients, a lot of them, expressed frustration towards me as a researcher about how fragmented the system is at Carney Center, and that causes delays in their applications for housing, for benefits, for ID, for everything, basically. At the same time, they really have limited awareness and knowledge of mental health resources, so they usually default to emergency care. As you would imagine, that would bump up local healthcare costs significantly. At the same time, they would also not able to access long-term treatment and recovery either. And then in terms of from the staff perspective, case managers report high risk of burnout. At the same time, because of limited funding, usually they only hire or they only have master level case managers, and these students graduate over time. Therefore, there's a high turnout. There's a high rates of people who are just coming and leaving, further decrease the continuity of care. And then in terms of technology use, it is true that nowadays everybody has a smartphone. However, we do found that some of our clients have limited data and digital literacy. By that, I mean when I conduct an interview and some usability testing with our participants, they were having difficulty navigating the laptop and able to figure out how to talk to our KC chat. In terms of chatbots specifically, although they did say it could be helpful for them to use chatbot to schedule clinical appointments. However, they do express doubts regarding whether chatbots can provide emotional support. And then they also express concerns for privacy and trust, not knowing how the data is going to be handled and where it's going to go after they start chatting with Casey. Leadership does say Casey as a triage tool, helping them to screen for mental health needs, to referring out to different services. However, some staff members did flag potential risks for misinformation, as in a lot of resources in the center sometimes can be quickly updated on the floor. However, if we were to have an AI system, we have to make sure that the information presented by KC chat are updated real time or as quick as possible so that we won't break the trust between the users, the clients, and our system. Okay, so theme for putting everything together. The current state, the reality is our staff are juggling so many multiple disconnected databases. The reality is also that they're mostly using paper pencil stuff, and therefore there's really a challenge in keeping track of where their clients are and dealing with high caseloads, imagining dealing with all the paperwork as staff members at Carnegie Center. It's really difficult, and therefore their time is very limited, so clients then report difficulty reaching them for immediate support. So the key gaps in terms of this interview, we found obviously all of this fragmented system lead to inconsistent care, and clients felt like they were neglected by the system, even though the reality was staff members were just too under stress to provide enough attention and support for our clients. And therefore, Casey could really come in as a helpful AI concierge in the sense that they can become a central information hub for referrals, triage, and maybe even helping our staff member to automate some tasks like notes taking, keeping track of clients' progress in housing applications. And overall, we hope to use Casey chat to improve the communication and continuity of care and reduce our complaints and frustration from our clients, and also improve their long-term quality of life. All right, key takeaways real quick. Overall, we definitely think we should personalize and customize experiences for users, even though this is true for all technology. However, for our population, we do have to pay attention to their relatively diverse education levels. Being able to provide some simplified interface with voice, offline, low literacy options could be really helpful. Also, human integration was something that was brought up over and over again in interviews, where people really want to escalate to real human case managers when there are questions that couldn't be dealt with by KC chat. And then trust and transparency, of course, is very important. So being able to prioritize user consent and control and clearly communicate how data is going to be used is very important. And then centralized information hub. Of course, this one I haven't mentioned, but Carnegie Center also provides a platform for outside providers like dentists, vision care providers to help come in and provide different clinical services for our clients. And so having an information hub could also serve as a centralized way for outside providers to register and organize coordinated care. Last one. So in terms of long-term rolling out, we're going to continue collaborating with our community partner and really hoping to iteratively testing and co-design everything with our users, with our stakeholders to make sure things are going to be embedded long-term. All right, so NWU is our community collaborator who is initiating this project, and Carnegie Center is our homeless shelter that we're working with. Thank you. And questions?
Any question? Okay, no question. Let's thank speaker. Okay, our last paper is predicting symptom flare-ups in female pelvic pain disorders with a multimodal digital biomarker.
How do I
My research in the generative AI for smart and
Oh, thank you. Okay. Hi, my name is Rebecca Cohen. I'm a medical student at the Icahn School of Medicine at Mount Sinai. Thanks so much for having me here today. Okay, so female chronic pelvic pain disorders such as endometriosis, fibroids, and dysmenorrhea affect 1 in 7 women in the United States. They are marked by unpredictable symptom flares, which include pelvic and abdominal pain, gastrointestinal symptoms, genitourinary symptoms, among others. Management is challenging due to limited understanding of pathophysiology and lack of reliable predictors. So wearable technology offers a unique opportunity to capture continuous real-world physiological data, such as HRV, and this can potentially provide insights into the predictors of chronic pelvic pain disorder flares. So HRV is a measure of autonomic nervous system function, and its metrics can be divided into time domain and frequency domain. So the time domain metrics measure the amount of variability in between beats. And a common metric is RMSSD, which is the root mean square of successive RR intervals. So the frequency domain metrics reflect patterns in how the rhythm of the heart rate changes over time. And common metrics include high frequency, HF, LF, and the LF over HF ratio. And these metrics are very important because they vary with physiological stressors and thus have been explored as predictors in various disorders. And this brings us to our research question. Can HRV metrics from real-time wearable and patient track data predict CPPD symptom flares? So a brief overview of our methods. This was a prospective observational study. We collected 90 days of data via an mHealth app and a Fitbit tracker. After various exclusion criteria, our analytic sample consisted of 5,221 person-level days from 104 participants. Our primary outcome was a novel flare week score, which our team developed because there's no consensus definition in the literature. Cosigner mixed effects regression was applied to HRV circadian features, including MESOR, which is the midline estimating statistic of rhythm, amplitude, and acrophase. And so for covariates, we included age, BMI, steps, sleep, and menstrual period, and random effects, we included participant ID and person-level amplitude and acrophase. Lastly, we used GPT-4o to explore additional trends in our data and see if we could predict symptom flares based on feeding GPT previous week's data, and that is currently in progress. So now let's take a look at the results. So this table shows the baseline demographic characteristics of our cohort. The average age was 35, and nearly half identified as white, and the average BMI was 26.5. Next, we assess the association between HRV metrics with the following week's flare score, as shown in the table here. So the key takeaways here are that in the week preceding a flare week, RMSSD's MESOR and amplitude significantly decreased while the acrophase increased. LF over HF's MESOR significantly decreased. Menstrual period was positively associated with RMSSD. Menstrual period, steps, and sleep were inversely associated with LF over HF. There was significant variance in the HRV between participants based on significant random effects. So lastly, as I mentioned, we used generative AI, GPT-4o, to explore trends in our data and predict pain flares. So for the predictive component on the right, we basically gave GPT weeks 1 through 3 of data for 10 of our participants and asked if it could use that data to predict whether week 4 was a flare week or not. And then we compared to whether the patient reported it was a flare week or not. And so we were able to have 70% accuracy with that, but notably we only gave 10 participants due to token limitations. So we're currently exploring ways to improve this prediction. So in conclusion, our study presents initial evidence that HRV metrics can predict CPPD symptom flares via nonlinear estimation. And this supports a promising use of real-time mHealth and wearable data in the context of CPPDs. With that, thank you all for your time. I want to end this by thanking all of my mentors and collaborators. I feel so grateful to learn from all of them. Any questions?
Any question? Okay, no questions. Thank you.
Okay, thank you.